My name is Nick Johnston, and I've been a meteorologist since 2004. Forecasting now is very different from where it was even a few years ago. It's a lot more accurate, and it continues to improve at an incredible pace. Study after study has shown this. But the purpose of this video is to discuss why, even today with all our technology and improvements, the weather that is forecasted can still, at times, be very different from what actually happens, or why the forecast can change dramatically even a few hours in advance. This well-known and much talked about phenomenon is a reality that many forecasters downplay and many members of the public grossly exaggerate. My hope is that this video can help close that gap and explain the hows and whys a forecast can be quote-unquote wrong. First, here's a little bit about my background. I graduated from SUNY Brockport with a 4-year Bachelor of Science degree in meteorology in 2004. I then worked in broadcast meteorology for about 12 years, working in Wichita Falls, Texas, where I was able to chase tornadoes, Burlington, Vermont, where I covered both severe winter weather and extreme flooding from Tropical Storm Irene, and then in Albany, New York, where I covered pretty much everything. Since leaving television in 2017, I have continued to produce a daily weather forecast on Facebook Live for the public. I recently went back to school and got an Associate of Applied Science degree in Emergency Management from Frederick Community College, graduating in 2020. I am proud to be a member of the Naval Reserve, serving as a METOC, or Meteorology Oceanography Officer, in the Information Warfare Division. I'm excited to be employed full-time as an emergency manager with the New York State Department of Environmental Conservation, where I am also a certified wildland firefighter, and serve as a member of the New York State Incident Management Team. Let's start with the word itself, meteorology. The word meteorology comes from Latin and can be split up into meteor and ology. Ology is simple. It just means the study of. But what about meteor? Obviously, meteorology has nothing to do with actual meteors, so what gives? The word meteor is derived from Latin meteorum, meaning atmospheric phenomena or anything in the heavens. So clouds, raindrops, sunshine, all of the above. So that is where the word comes from, the study of the atmosphere. Since the dawn of time, people have tried to forecast the weather, using the knowledge and tools available to them at the time. The earliest weather forecasting was based on observation and pattern recognition, followed by increasingly accurate and sophisticated instruments to directly and remotely measure the atmosphere, coupled with the ability to share that information with others in real time. From Aristotle to the New Testament to Evangelista Torricelli and many, many others, the science of forecasting has taken thousands of years to develop. Here is a quick timeline of just some of the milestone events that led us to where we are today with modern meteorology, beginning with the Babylonians, who started to use cloud observations to predict the weather, and ending with the launch of the first successful weather satellite in 1960. It's incredible to think how far we've come. This doesn't even include the dramatic technological advances that have occurred in the last 50 or 60 years. Thanks to the contributions of countless scientists over the years, we now know that our atmosphere is divided into 4 basic sections: the troposphere, the stratosphere, the mesosphere, and the thermosphere. The weather we experience is generated within the lowest 15 or so miles of the atmosphere in what is known as the troposphere. But even if we just stick to that lowest level, getting accurate measurements of temperatures, moisture levels, and wind speeds remains a challenge to this day. And 200 years ago, early scientists studying the troposphere were literally risking their lives to do so. Atmospheric observations began as early as 1749 in Europe with the use of a kite to carry aloft a thermometer. A few years later, in the American colonies, Ben Franklin conducted a very dangerous experiment by flying a kite near a thunderstorm to demonstrate the electrical nature of lightning. With the invention of hot air and hydrogen balloons in France in the early 1780s, scientists ascended aloft taking with them barometers, thermometers, and other instrumentation to investigate the structure and chemistry of the upper atmosphere. Manned ascents to study the upper atmosphere continued through the 1800s, but those early flights were very dangerous. Depicted in the picture on the right, in 1862, James Glaisher, left, and Henry Croxwell, right, the real-life inspiration for the movie The Aeronauts, ascended to an altitude of about 11 kilometers, or 7 miles, over Great Britain, and nearly died from the extreme cold and lack of air. In a later flight taken over Europe in 1875, 2 French aeronauts did die as a result of inadequate breathing equipment. The attempt to remove the risky human element is what eventually led to unmanned weather balloons with measuring devices in the early 1900s. Today, we have ways to observe the weather remotely. Building on the earlier works of German inventor Christian Holzmeier in 1904, Sir Robert Watson Watt submitted the first radar patent while working as Director of Radio Research at the British National Physical Laboratory in 1935. This radar was quickly adapted for both military and civilian applications. Pulse Doppler radar was introduced in the 1950s, leading to the WSR-57 radar, which stood for Weather Surveillance Radar of 1957. That became the go-to weather radar for over 35 years. Then in 1988, the United States constructed a network of radars called NEXRAD, using the new WSR-88D, which stood for Weather Surveillance Radar 1988 Doppler. Many WSR-88D radars are still in use today. However, beginning in 2010, some have been upgraded to what is known as dual polarization radar, which adds a vertical polarization to the traditionally horizontal radar waves in order to more accurately discern what is reflecting the signal. This so-called dual polarization allows radars to clearly distinguish between rain, hail, and snow, something the previous horizontal polarized radars struggled to accurately do, thus significantly improving the ability to spot hazardous weather. Then there are satellites. The first successful weather satellite, TIROS-1, which stood for Television Infrared Observation Satellite, was launched in 1960. That paved the way for GOES, or GOES, which stands for Geostationary Operational Environmental Satellite, which launched in 1975. That was a huge leap forward in terms of resolution and allowing continuous monitoring of weather over the United States. Satellites not only give us the big picture, so to speak, they also allow you to view invisible elements such as water vapor, view cloud cover both day and night, and allow you to view the temperatures of clouds, which can be very valuable in tracking storms. We even have ways to take measurements from the most violent storms on the planet. For example, the Air Force Reserve's 53rd Weather Reconnaissance Squadron, the world's only operational military weather reconnaissance unit. The term hurricane hunters was first applied to their missions starting in 1946, and that's still what they're called today. The hurricane hunters fly heavily instrumented planes that are basically flying laboratories to take atmospheric and radar measurements within tropical cyclones and large winter storms. They also utilize dropsondes, which are expendable weather recording devices designed to be dropped from an aircraft to measure atmospheric conditions as it falls to the surface. Now, one of the newer tools in the weather measuring arsenal is what is known as a sail drone. A sail drone is a wind and solar-powered unmanned surface vehicle, USV, capable of up to 12-month data collection missions on the open ocean. In 2021, Sail Drone 1045 spent 24 hours inside Hurricane Sam, collecting data from the edge through the eye wall of the Category 4 storm, while continuously providing near real-time data, images, and video of the storm via satellite. The vehicle survived sustained winds of over 90 miles per hour and waves well over 50 feet without a single sensor failure. How about another relatively new technology, weather apps? Used properly, this is a truly powerful tool, but it is important to know what weather apps currently can and cannot do. They have many strengths, but they also have weaknesses. Let's go with the strengths first. They have the ability to send you weather alerts when severe weather is approaching. That, coupled with the ability to have a radar in your pocket, is incredibly valuable and potentially life-saving. They can provide hour-by-hour forecasts, which can update throughout the day, providing information on temperatures, winds, and rain chances, even notify you when rain is approaching your location. And they can also give you updates on current conditions. But all of this can also lead to a false sense of security. First, they only work if you have reception or access to Wi-Fi. If you're out on a lake or hiking a mountain, they may not work when you need them most. It is also important to know that there is very little human involvement in the forecasts that are provided. The same thing that makes them super convenient also makes them prone to big errors and oversimplification. 99% of all weather apps are automated, run remotely from California or Georgia, and rely almost entirely on computer models. Without the human element, they have no ability to give context to the forecast. A computer programmer in Atlanta probably doesn't know a whole lot about the subtle topographical features that could have impacts on the weather in your town. Day to day, an app might work fine, but when the forecast really matters, it's usually best to get a local opinion. If you have a trusted meteorologist on TV who has lived and worked in your area for a long time, that might be a good option. But a safe bet is always to check with your local National Weather Service. With more than 150 offices across the U.S. and more than 2,000 meteorologists on staff, they are local, staffed with real human meteorologists, and their job is to keep the public safe. Thankfully, they are accessible on the web, they have an app, and a presence on both Facebook and Twitter to push out both alerts and potentially interesting climate information related to your area. But it's not always high-tech that wins when it comes to forecasting. By the start of the 1900s, weather instruments had developed to a point where they could be carried aloft by free, unmanned balloons. Such soundings could rise all the way through the troposphere, where all weather is generated, and reach the stratosphere, which was a much greater height than that achieved with manned balloons or kites, and with dramatically less risk. By the early 1930s, the first radio meteographs, or radiosondes, were being flown into the stratosphere. In 1937, the U.S. Weather Bureau established a network of radiosonde stations that has continued to the present day. Even now, the weather balloon remains the best platform for directly measuring temperature, wind, relative humidity, and pressure within our atmosphere. Weather balloons carry a payload called a radiosonde, which is tracked by specialized ground equipment. Twice a day, weather balloons are released simultaneously from nearly 1,000 locations worldwide. This includes 92 locations operated by the aforementioned National Weather Service in the U.S. and its territories. The balloons are typically released at 1200 and 0000 UTC, Coordinated Universal Time, which translates to 7 a.m. and 7 p.m. Eastern Standard Time. The balloon flights last for around 2 hours, can drift as far as 125 miles away from their launch site, and can rise to over 100,000 feet, or about 20 miles, into the atmosphere. Today, weather balloons are made with a natural, biodegradable latex to minimize the environmental impact. They are filled with either hydrogen or helium. As the balloon rises, the instruments will often experience temperatures as cold as minus 139 degrees Fahrenheit, extreme differences in air pressure, ice, rain, thunderstorms, and wind speeds of almost 200 miles per hour. A small transmitter on the radiosonde, powered by a battery, sends all this data back to tracking equipment on the ground every 1 to 2 seconds. By tracking the position of the radiosonde, we can also calculate wind speed and wind direction with height. Radiosonde observations remain the primary source of atmospheric data and serve several important purposes, such as the primary input for computer-based weather prediction models, the basis for local severe storm, winter storm, aviation, and marine forecasts, weather and climate change research, input for air pollution research, and they serve as ground truth for satellite data. Even with remote sensing data, such as satellites and radar, without the information from weather balloons, accurate forecasts beyond a few hours would be all but impossible. The data collected by weather balloons and radiosondes is plotted on a chart known as a SKEW-T log P diagram, seen here. It plots things like the temperature, shown in red, and the dew point, shown in green, along with the wind speed and direction, represented by wind barbs, on the right, with height. The basic form and function of this chart has not changed much since they began to be used regularly in the late 1940s. The chart you see here, in fact, is a real plot from the morning of April 3rd, hours before the super tornado outbreak of 1974. In a 24-hour period, 148 tornadoes ravaged a swath from Illinois to Ohio down to Alabama and Georgia, resulting in over $4.5 billion in damage by today's standards and 335 fatalities. At the time, it was the largest tornado outbreak in U.S. history, a record that was then broken in 2011. Speaking of 2011, this is the SKEW-T diagram from April 27, 2011. Notice that 37 years later, not a lot has changed. Shortly after this sounding was taken, a 3-day reign of terror commenced, with a record-breaking 360 tornadoes confirmed across 21 states, stretching from Texas to New York and into southern Canada. Ultimately, $10.2 billion in damage was reported, with 348 people dead and more than 3,100 injured. The atmospheric data collected by the weather balloons and plotted on the SKEW-Ts was critical in both historic cases in alerting forecasters to the severe weather potential hours or even days in advance, allowing early warnings to the public. But it is important to understand that while weather balloons and their radiosondes may be one of our best tools, they are far from perfect. The fact that they drift with the wind means they don't give an accurate vertical profile of the atmosphere over any given point. Speaking of that point, this is a map of the 92 balloon launch sites across the United States. 92 might sound like a lot, but you can see there are some huge gaps in coverage. The nearest balloon launch point from your location could be hundreds of miles away, leaving you to assume that the atmosphere where you are is similar, an assumption that could be very wrong. And while getting readings twice a day is great, the atmosphere can change dramatically in 12 hours, and there would be no way for you to know until the next launch. There are certain circumstances where up to 4 launches a day are authorized, but it's also worth noting that in March of 2022, it was announced by the National Weather Service that due to a global supply chain disruption of helium, many balloon launch sites in the U.S. would have to cut back to only 1 launch a day instead of 2, meaning that vital atmospheric weather data will only be updated once every 24 hours. Something like that can have a big impact on forecast model accuracy. One thing that has changed over the years are tornado warning lead times, which reflect the improvements in forecast accuracy. In the 80s, tornado lead time was between 4 to 5 minutes, barely enough time to gather the family and get to the basement, if you were lucky enough to have one. Today, lead times range from between 8 to 18 minutes, averaging 13 minutes, which is about 3 times better than it was in the 80s, providing ample time to get to a secure part of your house. A major contributing factor have been the improvements in radar technology, which enables meteorologists to more clearly recognize the indications that a tornado may have formed. In the 17, 18, and early 1900s, when tornadoes struck, there was little to no warning, unless you could literally see it coming. On March 18, 1925, at least 12 significant tornadoes hit a large portion of the Midwestern and southern United States. The outbreak included what would come to be known as the Tri-State Tornado, the deadliest tornado in U.S. history, and the second deadliest in world history. The 219-mile-long track left by the tornado as it crossed from southeastern Missouri through Illinois and into southwestern Indiana is also the longest tornado track ever recorded. In all, at least 751 people were killed and more than 2,300 were injured, making the outbreak the deadliest tornado outbreak, March 18th the deadliest tornado day, and 1925 the deadliest tornado year in U.S. history. The Tri-State Tornado is recognized by most experts, including Ted Fujita himself, the creator of the Fujita scale, as an F5 tornado with winds possibly in excess of 300 miles per hour. Moving at a remarkable average speed of 62 miles per hour, and at one point a record tornado speed of 73 miles per hour as it approached Murfreesboro, Illinois, with this tornado, there was no warning for the communities that lay in its path, which is one of the reasons, aside from its incredible strength, that it was so deadly. Murfreesboro, seen top right, was completely blindsided, and of the 751 total people killed on that day, 234 died in Murfreesboro, a record for a single community from such a disaster. Many were caught outside. The bottom right is the picture of the Longfellow School in Murfreesboro, where 17 children were killed. In nearby DeSoto, Illinois, a record-breaking 33 children were killed when portions of their schoolhouse collapsed. Because the tornado struck at around 2:30 p.m., many children were still in school, and many people were out walking the streets. Okay, we've talked a lot about the history of forecasting, some of it fairly brutal, the tools involved, and some of their limitations. Now, I want to spend some time discussing the different types of precipitation and impacts. Regardless of the time of year, weather is one of the most impactful aspects of life on this planet. In the Northeast, these impacts are perhaps most pronounced in winter, when people really rely on the forecast. Even a coating of snow can be dangerous, especially if it is unexpected. Have you ever wondered why it always seems like it is so hard to get the forecast right in the wintertime? Meteorologists predict 3 to 6 inches of snow, and you end up getting 8 inches of light, fluffy snow. Or the forecast calls for 3 to 6 inches of snow, and it ends up being 1 inch of snow and sleet with rain mixed in. How can this still be happening with all of our technology? Clearly, meteorologists are just collectively bad at their jobs, right? Well, the reality is it comes down to what they can't see. We have weather stations on the ground, lots of them, that can measure pressure, temperature, dew points, humidity, wind speed and direction, etc., etc. But as discussed, when it comes to the 20 miles or so of weather-producing atmosphere above us, the troposphere, we have very limited ability to know what is really happening at any given time. We get weather soundings, hopefully nearby, typically twice a day, but a small change in the temperature of the atmosphere at 10,000 feet could have a huge impact on what happens on the ground. In the summer, a small change in the temperature of the upper atmosphere usually doesn't impact much, maybe a few extra clouds, or maybe a quick unexpected shower. But nothing like the difference between expecting rain and waking up to heavy snow, or expecting a big snowstorm and waking up to rain. Let's review real quick the 6 main types of precipitation from left to right. There is hail, rain, freezing rain, sleet, snow, and can you identify the last image on the right? That one is less common and typically occurs in either spring or fall. It's known as GRAUPEL. The reason GRAUPEL is so rare is that it takes very special conditions for it to form. There has to be a mixture of frozen and non-frozen water in the cloud. That's why it tends to happen in either spring or fall. In winter, the upper atmosphere is typically too cold, and in summer, the surface is usually too warm. GRAUPEL showers usually only last a few minutes. It also typically melts fairly quickly, because it almost always happens when temperatures on the ground are above freezing. So here's how it forms. You start off with an ice crystal in a cloud, but while suspended, that ice crystal encounters tiny drops of supercooled water. That's pure water that has a temperature below 32 degrees. Those drops of supercooled water instantly freeze when they come in contact with that ice crystal, turning what would have been a snowflake into a tiny round ball. Ultimately, it looks like a tiny packed snowball, but it is still light like a snowflake, and not a hard piece of ice like sleet or a hailstone. GRAUPEL may be less common, but in winter, even the more frequent forms of precipitation rely on very subtle changes in temperature at different levels of the atmosphere. The difference in terms of impact between rain, sleet, freezing rain, and snow is huge, but the difference as far as the atmosphere is concerned may be as little as 1 degree over 1,000 feet. Generally speaking, if the temperature stays at 32 degrees or below throughout a column of air, you've got snow, as seen here. Sounds simple, but it's not. Technically, near the surface can be above freezing, and depending on how warm, how deep, and how heavy the precipitation is, you can still get snow even with temperatures in the mid to upper 30s. It just becomes heavier, wetter snow. However, if the layer at the surface is warm enough, deep enough, or the precipitation is light enough, it can allow the snow to melt completely and land as rain, or land as wet snow that then melts on the ground. Big difference. Compare that to if the entire column of air, including the surface, is very cold, and you will get a much lighter, fluffier, and drier snow. Complicated, and that's just for snow. Let's talk a little more about that wet versus dry snow with a concept known as the water-to-snow ratio. Temperatures determine whether it is a wet or dry snow that falls, and that can have a huge impact on how much accumulates at the surface. Most snowstorms have a water-to-snow ratio of approximately 1 to 12. That's to say that 1 inch of water equals 12 inches of snow. But the warmer it is, the lower the ratio, and the colder it is, the higher the ratio. So if that temperature is above freezing, but not warm enough to melt the snow into rain, the ratio of water to snow can be as low as 1 to 5, where 1 inch of liquid equals 5 inches of snow. Think of a heavy, wet snowstorm in March with 10 inches of back-breaking, wet, cement-like snow. Whereas a very cold snowstorm with temperatures, say, in the lower 20s, could result in a very high liquid-to-snowfall ratio of 1 to 20, where 1 inch of liquid equals 20 inches of snow. Picture a cold, breezy January snowstorm where you wake up to 2 feet of light, dry, fluffy snow. Easy to clear, but very deep. It all comes down to the temperature profile of the atmosphere, and small changes in temperature can have huge impacts on the ground. What if the temperatures at high altitude are above freezing, enough to form rain, but the temperatures at the surface are cold, 32 degrees or below? Well, depending on how deep that layer of cold air is at the surface, you will either get sleet or freezing rain. If those freezing surface temperatures are more than 1,000 feet deep, the raindrops have time to freeze into small ice pellets as they fall, known as sleet, as shown above. If, however, those freezing surface temperatures are shallow, less than 1,000 feet deep, the precipitation will most likely fall as rain, then freeze on whatever it lands on, freezing rain. Sleet creates brutal driving conditions, while freezing rain is extremely dangerous for power lines, trees, and crops. This change can happen over relatively short distances, making conditions unpredictable, and anyone who lives in a hill town can tell you that a small rise in elevation can have a major change in what type of precipitation occurs and in what quantity. Finally, even if the precipitation starts as ice crystals in the high atmosphere, which can happen even in summer, as long as the column of air to the surface is warm enough and deep enough, the precipitation will fall as rain. I described these differences to impress upon you how complicated it can be to predict what type of precipitation will occur, in what location, for how long, and at what intensity, particularly when you typically only get accurate measurements of the atmosphere twice a day, assuming you are lucky enough to have a balloon launch site near where you live. When it comes to faulty forecasts, in upstate New York, one event stands out: the October 4th snowstorm of 1987. What was forecasted to be a cold, rainy day ended up being a devastating snowstorm with between 6 inches and 2 feet of extremely wet, heavy snow falling across much of the capital region and surrounding areas. Now, that much snow is not necessarily a big deal in upstate New York, unless it happens on October 4th, when all the trees still have their leaves. Even if the storm had been properly forecasted, there may not have been much that could have been done to prevent the damage. But it did catch both the public and area forecasters by surprise. Roughly 250,000 people were without power, some areas for as much as 2 weeks. The storm also proved to be fatal, with some 20 storm-related deaths, several from falling trees, and roughly 300 injuries. Smashing records along with millions of trees, this heavy wet snow event was not only the single greatest snowfall ever to happen in the entire month of October, but incredibly, it is also still the earliest that snow has ever fallen in Albany. Scenes like this one here were widespread. One witness stated that once or twice a minute you could just hear loud pops that sounded like firecrackers going off. But it was trees snapping in half, often taking power lines with them. That witness was 5-year-old future meteorologist Nick Johnston, seen here playing with my sister Emily in our backyard in Albany. Keen observers will notice broken trees in the background. The fact that I am using a metal digging shovel because traditional snow shovels were breaking under the weight of the snow, and perhaps also the fine craftsmanship of the snowman, who even has snow arms. This is because snow that wet can basically be molded like clay. Incredibly, during the entire 12-hour event, the temperature never dropped to 32 degrees. The coldest it got was 33. But what was happening in the atmosphere, not at the surface, made this incredibly unlikely storm possible. A look at the 3-day timeline demonstrates the unlikely nature of the storm. The normal high temperature for that time of year is 67 degrees, and the normal low is 45. The day before, the high temperature was 60, and the day after was 61. Even the day of the storm, the high temperature of 45 degrees would suggest it was warm enough that snow would have been unlikely, and the precipitation amount of 2.82 inches is enough to think that flooding might have been a concern, but not snow. Some of that did fall as just rain. But while snowing, the liquid to snowfall ratios were reported at a staggeringly low proportion of 1 to 3.5, meaning that for every 1 inch of liquid, it was translating to only 3.5 inches of snow. Remember that typical snowstorms have ratios of 1 to 12. So the next 2 slides are a summary of why it was a faulty forecast. For a lot of reasons, this was an extremely difficult storm to have correctly predicted. At the time, there was no historical context, as a storm like this had never happened before or since. Climatology said it shouldn't happen. Recent weather made it unlikely, with warm temperatures, unfrozen ground, and moderate rain with lingering puddles. The weather equipment contributed to the problem. The forecast models missed some key information, such as significant cyclogenesis off the coast, when the precipitation would start, and the intensity of the precipitation. Melting snow made it difficult to measure accurately. Big gaps in snow reports and spotter networks in hard-hit areas meant measurements were few and far between. And making matters worse, because of how early in the season it was, snow plows hadn't been fully outfitted, making the cleanup much slower than it should have been. Then there's the complex nature of the storm itself that made for some incredible forecast challenges. This was an extremely temperature and elevation-sensitive storm, leading to some dramatic differences over short distances. As an example, Albany got 6.5 inches of snow, while Winenskill, only 6 miles away, got 22 inches. Snowfall rates at times were estimated to be a blinding 5 to 7 inches per hour, which is nearly unheard of. Likewise, with liquid-to-snow ratios as low as 1 to 3.5 inches, that is very unusual, and something you might not think of, the timing. Because the storm happened on the weekend, Saturday night into Sunday, forecast offices had less staffing and fewer senior members. And then the forecasters themselves simply missed a few things. The temperature forecast was too warm. They did not predict the development and persistence of a cold dome effect at the surface, and they did not anticipate significant diabatic cooling aloft. Simple mistakes to make, but in this case with major impacts. So the big question is, could this happen again today? And I would say the short answer is yes. Sure, technology has come a long way, and so has emergency planning, in part due to lessons learned from storms like this. Radar technology has improved significantly. Model forecast accuracy has improved. Surface observations and spotter networks have improved, and forecasters have gained valuable knowledge from studying storms like this. So big misses like this one should happen less and less. But a similar storm today would still be very difficult to diagnose. Given the highly complex and sensitive nature of the storm, a detailed snow forecast would still be very hard to pin down. Staffing is still sparse on weekends, and often with less experienced forecasters. Forecast models still make large mistakes based on faulty assumptions, and it is common for two forecast models to have wildly different forecasts. And ultimately, the most important tool in determining precipitation type, weather balloons, and radiosonde data, really hasn't changed and is still only offered twice a day. For me, forecasting the weather reminds me of the idea of significant figures from grade school science class. Significant figures relates to the precision with which something, such as length, temperature, pressure, volume, or mass, can accurately be measured, given the measurement resolution of an instrument. Here's an example. Notice the ruler on top. The smallest denomination of measuring units are centimeters. Significant figures includes all known digits plus one, and only one, estimated digit. If you were trying to measure this pencil, you could say that it is 5.6 centimeters, one digit that you can clearly see, 5, and one digit that is reasonably estimated, 0.6. This yields two significant figures. The ruler below is more precise. Its smallest denomination of measuring units are millimeters. So if you were using that ruler, you'd get a more detailed measurement of, say, 5.62 centimeters. Two digits that you can see, and one digit, the 0.02, that is estimated. This yields three significant figures. It all depends on the level of detail needed and the precision of the equipment you have available. Imagine trying to measure the width of various strands of hair using a yardstick. Rounding to the nearest significant figure, you'd always get 0. In some ways, the weather forecast can be a little like this. Some storms are easy to predict, but some storms with multiple complicating factors simply get beyond the range of what can reasonably be resolved. The equipment and data available simply can't get that level of precision that the public, understandably, demands. If nothing else, that is the point I wanted to make. Meteorologists, as a rule, always do their best to forecast as accurately as possible. It can be hard for meteorologists to admit that some storms are beyond what can reasonably be forecasted with high accuracy. Oh, they'll give it their best shot, but even today, Mother Nature has enough atmospheric cover that she is sometimes able to still sneak up and do something unexpected. In conclusion, with the help of innovation and technology, weather forecasting has come a long way and continues to improve. It is possible to imagine that in the not-too-distant future, we may have the ability to accurately scan the atmosphere in real time. Supercomputers will then be able to process that vast amount of data in fractions of a second, and little, if anything, will happen that isn't predicted with near certainty. But currently, on occasion, Mother Nature creates a storm or set of circumstances that computer models can't anticipate, and even the most seasoned forecaster has a hard time figuring out. Even with all our amazing technology, there are still situations that require filling in the gaps with educated guesses. Many times, those are right, but sometimes those are wrong. And rest assured, those are the ones that the public never forgets. Thanks for watching, and have a great rest of your day.